Good evening, everybody, and welcome to Lecture 15, where we start to move on, at least for the moment, from our focus on Antarctic history onto anthropogenic climate change, starting with, in this lecture, a broad overview of the science behind climate change and how it has affected the world in general, as well as what's causing it. And then in Lecture 16, we will have a more detailed examination of how it has affected Antarctica. And this unit builds a fair bit on previous Antarctic science that we've learned, like the climate science that we learned about during week 2, as well as the Antarctic ecology that we learned about during week 4. Because we're talking about how the climate and the ecology have been affected by climate change. And in a way, this continues the history of Antarctica by discussing the impact of anthropogenic climate change in the 20th and 21st centuries, although we'll talk a little bit more about the human history in one lecture that we have later next week. I wanted to keep the two climate change lectures grouped together. So next week, we will indeed have one final lecture of new material that covers the human history of Antarctica since the Heroic Age and puts some facts about modern Antarctica, like tourism and the Antarctic Treaty, into the context of what we've learned previously. But for now, let's talk climate change. So lecture quiz number 2 is open, and that's probably the most important matter of business right now. It will remain open until Sunday, May 23rd at 11:59 p.m. And it does not cover either this lecture, Lecture 15, or Lecture 16. So it covers Lectures 11 through 14, which are on glaciers and the history of Antarctica, but it does not cover the climate change lectures. You will also want to make sure that you've seen the relevant clips of Encounters at the End of the World and Antarctica: A Year on Ice, and that you've skimmed the Shackleton excerpt. I am not asking you detailed reading comprehension questions about the Shackleton excerpt. Just make sure that you've at least skimmed through it at least once. So that review session for this quiz was supposed to happen today. Circumstances outside of my control meant that I couldn't be around Zoom in the middle of the day, so it is happening on Wednesday during normal office hours, starting at 2 instead, and I will be around to answer questions until 4 that day. I do really apologize for the change in scheduling. And setting that aside, reading assignment number 2 is due a week after lecture quiz 2. It is due on Sunday, May 30th at 11:59 p.m. I've seen a few people have submitted that already. It is a good thing to get taken care of as early as possible, because after the deadline for that hits, it'll be dead week and we'll be talking final exam preparation. There is also a lab on Antarctic exploration to do this week, and that is due on Friday, May 21st. For that, I recommend reviewing lectures 13 and 14, as well as going back to reviewing the geography lecture, lecture 2, because this lab has a fair bit to do with maps and latitude and longitude come up again. Lastly, there are a couple of extra credit opportunities occurring this week. We have 2 graduate students at UCSB presenting about their research related to seismology. One of them actually has an interesting application to the COVID-19 pandemic, which I find really interesting, but Han Xiao, who has actually TA'd for me before, so you can consider this going a bit of a sign of support for someone who's TA'd for me, or Lun Shang. Both of those 2 are going to be presenting at the colloquium on Thursday, May 20th at 2:00 p.m. And again, since there's 2 people presenting during about an hour period, you can write about half a page about each of them, like 200 words ish about each of them, if you decide to attend this for extra credit. And there is also a UC Santa Cruz seminar happening on Friday, May 21st at 12:00 p.m., also about earthquake waves. So seismology is all about the study of earthquake waves and their applications. So actually both of the 2 events happening this week that you could do extra credit for are related to earthquakes, which is cool. But anyhow, if you remember that the points go to your midterm, you can do extra credit a total of 3 times per quarter, and each assignment that I accept gives you 3 points, and I can add points retroactively to your midterm. I can also sort of keep points in reserve for your final exam. So keep that in mind. It's not too late to do extra credit, obviously. Points can be added to your midterm after the fact. Anyhow, a quick overview of lecture quiz number 2. It's very similar in format to the previous quiz. It will consist of 10 multiple choice and true or false questions that are automatically graded, as well as 1 or 2 short answer questions that the TAs will grade. And you have 30 minutes to take the quiz. You need to finish your attempt by Sunday, May 23rd, and the review session on Wednesday, May 19th will cover quiz material. And nothing that we covered before the midterm will be explicitly tested on for this quiz, nor will lectures 15 and 16. So you don't need to worry about reviewing pre-midterm material for this. Review lectures 11 through 14, and remember that on the past quiz that the short answer questions had a fair bit that was related to the articles and the videos. So expect similar questions to show up related to encounters at the end of the world or the Shackleton reading. I'll see with the Shackleton reading, I'm not going to ask you detailed questions. That's just kind of there because expect questions about Shackleton to show up. Let me put it that way. And I will talk more in depth about the format of lecture quiz number 2 during the review session on Wednesday, which I will record and release for those of you who cannot necessarily attend it live. And again, I do apologize for the change in schedule. So let's talk a little bit about today's material. Some of today's material will be a retread because we did cover concepts like greenhouse gases before, but we'll talk more in depth about their effect on climate and how human activities have caused levels of greenhouse gases to skyrocket. The second half of the lecture will deal with the concept of the carbon cycle, examples of feedback in climate change, and we'll start to get into some broad effects of anthropogenic climate change. So I hope that one takeaway that you had from lecture 3, way back in the course, was that climate and weather are not the same thing. Weather refers to measurements like the temperature, the pressure, and the humidity taken for a single day, or possibly even a single point within a single day, like temperature as it varies on the hour. And weather is data. It's a few data points. A few data points doesn't necessarily give you the whole story or the overall trend. And climate is the long-term averages of these data. Average annual temperature ranges, average rainfall, average air pressure, etc. And the climate of a given area is generally going to be stable within our lifetimes. This is an assumption that is falling apart now, that rapid human-induced changes are being factored in. But under normal conditions, climate remains stable over the lifetime of humans and other living organisms. It will change over geologic time, normally on a scale that's not easily observable to people. And climate is regulated by a number of different factors, but in general, on a scale of less than 1 million years, the primary influences are going to be the amount of solar radiation that reaches the Earth as a product of Milenkovic cycles, or changes in Earth's orbit and tilt and the direction of the wobble, and we will review that in this lecture. In addition to Milenkovic cycles, greenhouse gas concentrations vary on a scale of thousands or hundreds of thousands of years, and they also have a significant effect on climate. On a scale greater than 1 million years, plate tectonics play an important role, and we'll talk about how the amounts of volcanism occurring on Earth, more volcanoes means more CO2, for example, and how decreased amounts of volcanism can cause long-term climate change. We did reference this a little bit, actually. Remember how when we talked about snowball Earth during the geologic history of Antarctica section, I indicated that the snowball Earth period was brought to an end when more subduction caused more volcanoes, which caused lots of CO2 emissions, which helped build CO2 up and build greenhouse gases up and help Earth get a bit warmer again. So the main place where that factors in actually is the cycling of carbon, and we'll talk about the carbon cycle during the second half of the lecture. So Earth is presently officially in an ice age because an ice age is defined by the presence of any ice sheets. Right now, we are in what is known as an interglacial period. We still have ice, but the ice is at a small extent of its potential maximum. Um, this, as I hope this diagram indicates, much of the land in the northern hemisphere that is now sort of temperate woodlands and conifer forests, that was completely covered in continental glaciers, in ice sheets, large continental glaciers. And the point of this is that the ice sheets used to be more extensive than they are now, and also sea ice around Antarctica was more consistent, and the ice shelves went out farther. And that is what is known as a glacial period, when during an ice age, the ice sheets and the ice shelves are at their greatest extent. We often use the term the Ice Age to refer to the period in which mammoths and woolly rhinos and ground sloths and saber-toothed cats existed in a colder and much more heavily glaciated landscape alongside early humans. And that is actually more the most recent glacial episode of the ongoing Ice Age, of which we are in an interglacial period. So an interglacial period is not the absence of ice or a period outside of the Ice Age, and one great irony is that without human-caused or anthropogenic greenhouse gas emissions, we would likely be headed towards another glacial period of the exact same Ice Age, and that would happen quite soon, geologically speaking. And for example, one speculative program about future evolution that I once saw called The Future is Wild, which was imagining a post-human world, essentially, proposed a world 5 million years from now in which humans had gone extinct through unclear reasons, and the world was dry, cold, and inhabited by creatures like these giant whale-like birds, gannet whales. And that's one thing to consider, actually, when we talk about the Antarctic record of climate change. The glacial episodes are drier because more water is locked up in the ice sheets, and that's an important factor that we'll talk about when we talk about climate records later. But anyway, it's fascinating to think that this might have been, or that something like this might be what would happen if current greenhouse gas emissions weren't making the world warmer. Of course, programs like this are fiction. So in the current interglacial period, humanity has changed Earth quite a bit. And the rise in the emissions of greenhouse gases and the atmospheric concentrations of greenhouse gases, that can be pinpointed to the late 18th century. The late 18th and early 19th century, the Industrial Age. And the term the Industrial Revolution refers to a rapid mechanization of labor and the rise of factories and manufacturing, as well as automation and the compartmentalization of labor, like the assembly line process. All of this involved a rapid increase in the use of fossil fuels because all of these machines required energy, and burning oil and gas and coal provided that energy. It involved also the development of mechanized transportation like trains and cars, and eventually airplanes that also use significant amounts of these fossil fuels. And again, there is nothing inherently wrong with factories or cars or airplanes, but all of these need energy to operate. And just about everywhere in the world, whether it was the United States or Western Europe or Australia or China or Japan, coal very quickly became a favorite source of fuel because it was relatively abundant. It was, at least early on, relatively easy to access. Of course, now a lot more coal is being mined from deeper, and it's getting harder and more expensive to mine, and also more environmentally destructive. Coal is everywhere in the world because I mentioned that these swamps that actually produced the coal existed during what is known as the Carboniferous period. Shortly after the colonization of the land and a bit before the Permian extinction. And we have that in Antarctica. We actually have coal in Antarctica that formed as the fossilized remains of these swamps. So the coal found in Antarctica or West Virginia or Gansu, China is largely all from the Carboniferous period. And the people have always known that coal existed, but it became much more valuable during the Industrial Revolution because now money and success lay in lay in machinery, and that coal provided a extremely valuable source of energy. And oil, so coal is, the reason coal is useful for energy is because it is made of hydrocarbons. And the chemical bonds in those hydrocarbons have a lot of energy, so burning them releases that energy and makes it available, at least to some extent, for people to use for machinery. And again, coal also was quite abundant and easy to extract early on. Oil also came into much more widespread use because people realized it could be refined into fuel for cars, as well as fuel for trains later on and for airplanes. And so oil consumption skyrocketed, and oil extraction became an important industry, and became a key facet of the world economy. So coal, oil, and natural gas, which forms alongside oil, are collectively known as fossil fuels because of their origins as dead living organisms. Natural gas and oil are formed from dead phytoplankton, and coal is formed from dead swamp plants. And now just about every facet of society is dependent on fossil fuels for transportation and heating, and for generating the electricity needed for just about everything. And of course, people didn't realize this at the time because climate science hadn't really progressed to that point. But the 19th century is where the charts of carbon dioxide concentrations start to go off the charts. They wander outside of what scientists have established would be the normal range of carbon dioxide concentrations if the human influence of burning fossil fuels were not involved. And how do we actually know what atmospheric CO2 concentrations have been like over the past centuries and thousands of years if we didn't have advanced climate records then? It turns out that we can actually obtain that information from ice cores. And I hinted about that earlier in the course, and we will talk about that in a lot more detail during lecture 16. Now, there is a lot of course, there are a lot of people who deny that the increases in temperature that we're seeing today are driven by this, that they're driven by an increase in CO2 released from people burning fossil fuels. And there are indeed non-anthropogenic factors that control climate. You might be familiar with some of the counter-arguments to climate change being anthropogenic, and you might have heard people invoke sunspots or invoke changes in Earth's orbit, and that is them referring to Milenkovic cycles. Let's first address sunspots to debunk the idea that they really have anything to do with the current climate change. So when we talked about climate before, I largely focused on how much solar energy was reaching the Earth without really dealing with how much energy the sun itself is actually putting out. And there are indeed actually variations in the amount of radiation and thus the amount of energy that the sun actually puts out. And sunspots, which are visible on pictures of the sun as these little black dots, those are portions of the sun that are relatively cool. And it's not so cool that you would want to touch it. You would die if you touched it, but we're talking about 3,800 degrees Kelvin as opposed to 5,800 degrees Kelvin. So noticeably colder, but not quite as blazing hot as the rest of the sun. Think sort of hot, dark coals versus blazing red or white hot coals. The glowing coals are hotter. And sunspots come and go in a cyclical pattern. There seems to be a maximum in the amount of sunspots every 10 years, and some climate change skeptics have attempted to invoke sunspot cycles as an alternative explanation for global warming. It sounds like a good explanation until you look at the data and how the timescales match up. Don't worry about what every trend line means here, but collectively this indicates that the maximum output in solar radiation occurs every 10 years. You have maxima in 1980, 1990, and 2000-ish, and likewise you have low points in the amount of solar radiation in 1985, 1995, and 2005. Now, 2005, in which the radiation was at a minimum, was not particularly cold. It was actually cited as the warmest year in over a century by NASA. So sunspot cycles, which are cyclical, don't align with the upward trend in temperature that we've seen happening in the past couple of centuries. And this is what I mean by sunspots. Don't look at the sun directly. This is from a telescope. But anyhow, sunspots are the colder spots on the sun, and they don't have anything to do with the current climate change crisis, because the amount of sunspots is not decreasing over time. It's not that we don't have like lots fewer sunspots and that's what's causing things to get warmer. It does not line up, and it is not a good argument. So let's next address Milenkovic cycles, and I'll discuss them a little bit more in detail here. If we set sunspots aside, the amount of solar radiation emitted by the sun over the course of centuries and millennia, if you average it out, is pretty consistent. On the scale of tens of millennia, however, Earth experiences some variations in its orbit that can have a major effect on climate. And it's really hard to seriously argue that Milenkovic cycles can be that Milenkovic cycles can be responsible for the changes that we're seeing today. We've seen temperatures rise over the course of just a few centuries, and the temperature increases begin around the time of the Industrial Revolution. That's when the consistent upward trend in both temperatures, as well as carbon dioxide and other greenhouse gas concentrations, begins. Now, Milenkovic cycles could cause climate change on a much more gradual scale over the course of thousands of years, on a scale that humans would not really easily be able to notice. The first Milenkovic cycle is eccentricity, and Earth goes between having a more circular orbit or low eccentricity, or having a more oval orbit or high eccentricity. And this period, points of greatest eccentricity occur about every 100,000 years apart. And this has the potential, so this cycle has the potential to affect the duration and the intensity of the seasons because it affects how close the Earth is to the sun at different times of year. But it isn't going to occur on a fast enough scale that it could really explain why the temperatures are going up all of a sudden now, over something happening in the past couple hundred years. The tilt refers to the degree at which Earth's axis is tilted. Remember that Earth is not straight up and down, the axis is tilted, and that's actually plays a role. That's actually what causes seasons, and it's also what causes Antarctica to be in 24-hour daylight for part of the year and to be in complete darkness for much of the rest of the year. And remember that the Antarctic Circle, which is the line of latitude below which all of the areas experience at least one 24-hour period of darkness and one 24-hour period of complete continuous sunlight per year, the location of the Antarctic Circle changes over geologic time with the tilt of Earth's axis. Hypothetically, this could affect and so the changes in tilt are going to affect Earth's climate because where the Antarctic Circle is going to affect climate. But this occurs on a scale of 41,000 years, so not really relevant for modern climate change. And the last Milenkovic cycle is precession, which also somewhat relates to the tilt of Earth's axis, because if we set aside the angle of the tilt, the hypothetical line along Earth's axis from the South Pole through the core to the North Pole points in a particular direction out in space, such that the line is looking towards different stars, essentially. And one way to think about it is kind of like how a top or a dreidel, that if the handle on the top or the dreidel will point in different directions as the device is spinning around. And Earth's axis is pointing in different directions over geologic time. And if Earth starts at this point, it will be back pointing at that particular orientation in 23,000 years. Again, also not on a scale that can really be invoked to explain any of the changes we're seeing right now. Studying Milenkovic cycles and relating changes in Milenkovic cycles to climate is complicated because it's difficult to directly assign particular climate events to Milenkovic cycles. It appears that when all three cycles are taken into account to produce a number that stands for the amount of solar radiation received by the Earth. Periods in which the combined Milenkovic cycles result in lower average solar radiation reaching the Earth correspond roughly to the glacial periods in an ice age. And in the diagram here, you can notice how the troughs in the combined signal on the diagram correspond to periods in which another proxy for climate studies, or the oxygen isotope ratio in marine sediment, drops, which indicates glaciation, and that's something we'll talk about more. Now, Milenkovic cycles alone do not cause an ice age. Milenkovic cycles have been operating on Earth for years, and Earth has not always had any ice at all. During the Cretaceous period, when Antarctica and Australia were close to the South Pole, there was no polar ice cap at all. And Milenkovic cycles went on during that period. So outside of Milenkovic cycles, plate tectonics, average global albedo, and greenhouse gases have to be considered as well. So in short, Milenkovic cycles control climate, but it's not a direct cause and correlation thing, and it's also on a very, very long time scale. Now, we've talked about greenhouse gases a little bit before when we spoke about atmospheric chemistry and atmospheric circulation. And greenhouse gas is a term for a gas that has a molecular structure that allows it to absorb infrared radiation. And when this happens, the infrared radiation will again be released by the greenhouse gas molecule. It'll be released in all directions, and some will go up and out into space, but part will go down and back to Earth's surface, where it will continue to warm the air and warm the land. And common greenhouse gases include water vapor, carbon dioxide, methane, and nitrous oxide. Overall, they are not particularly abundant when you consider their absolute concentrations. Collectively, greenhouse gases make up about 1% of the atmosphere, and concentration of carbon dioxide is not expressed in percents usually. It's expressed in parts per million, which is essentially percents, but with numbers out of a million. So 2 parts per million basically means that well, 2 out of those 1 million, if you take 1 million molecules within a sample of air, 2 out of that million will be CO2. So that tells you that there's not very much CO2 present. We express it in parts per million rather than percent because there is less of it. And that's true of all of the greenhouse gases. However, something that I've observed in general is that when there's stuff present in very trace quantities on the scale of parts per million, changes in the quantities of those substances can be quite consequential. For example, in our bodies, we don't need very much iron, but minor variations in the amount of iron can cause anemia. We don't have much iron in our bodies overall, but if the amount changes too much, then we can get anemia and suffer horribly. And the Earth is quite sensitive to changes in greenhouse gas concentrations, even of a few parts per million. The main function of greenhouse gases is to control how much heat can leave Earth's atmosphere. If we had no greenhouse gases whatsoever, so much radiation would escape that the planet would be frigid and uninhabitable. What greenhouse gases do is they increase the radiative forcing, and that is the difference between the amount of energy absorbed by Earth as sunlight and the amount emitted to space. If there are a lot of greenhouse gases, less energy will make it back out to space, and that will increase the difference and make a larger radiative forcing. So when people talk about the radiative forcing increasing, they are talking about global warming. And water vapor, which I mentioned briefly, is indeed a greenhouse gas. It has a chemical structure in which it can absorb and re-emit infrared radiation wavelengths. And by weight and volume, it is the most abundant greenhouse gas in the atmosphere. However, it is not normally invoked as a contributor to anthropogenic or human-caused climate change because burning fossil fuels does not release a significant amount of water vapor. And the amount of water vapor that's being added to the atmosphere overall has not changed significantly since the Industrial Revolution. In addition, water vapor has a shorter residence time in the atmosphere than carbon dioxide and methane, and the other greenhouse gases because it is involved in just so many different chemical, biological, and geological processes, and it has less potential to build up. However, how much water vapor is present in the atmosphere in a given area is going to be affected by changes in weather patterns, and those changes in weather patterns have largely been caused by increases in CO2. If an area becomes more or less rainy, that's going to affect the overall humidity of the atmosphere over the area. Now, so carbon dioxide is produced by burning coal and oil, and it's been the increases brought about by carbon dioxide have been definitely of concern, and they're the most prominent because fossil fuels are now such an intrinsic part of how society functions, and there's been a lot of resistance to moving away from them. There's a lot of money and political will built into keeping fossil fuels a part of the infrastructure and economy, and so CO2 emissions have thus been hard to kick, shall we say. And carbon dioxide is going to be emitted by any process that burns fossil fuels, whether that be a coal-fired power plant or whether that's a car burning gasoline. And carbon dioxide can absorb several different wavelengths of light. And one thing to observe is that the molecules, they'll kind of dance and change shape. They'll bend, they'll twist, they'll flip. And what the molecule is doing when it flips or bends is it's absorbing the light, it's absorbing the infrared radiation, and then re-emitting it. And the energy that gets released back to Earth by CO2 doesn't make it out to space. It gets retained in Earth's system, in the atmosphere and the oceans. To some extent, that is necessary because greenhouse gases keep Earth habitable, but in excess of them causes global warming and causes changes in weather patterns, including stronger hurricanes and flooding that can be devastating, as well as melting of ice sheets. CO2 varies according to a number of processes that we'll talk about more during the second half of the lecture when we address the carbon cycle. Now, concentrations in carbon dioxide have varied year to year, but until 1950, they never exceeded the mark of 300 parts per million. And this was over the entire course of human existence. Even during any portion of the current warm or interglacial period, CO2 levels in the atmosphere never exceeded 300 parts per million. And you can see if you look closely at this diagram that this is on the scale of hundreds of thousands of years, but close to the present, it has just begun shooting up. And you'll notice this kind of wiggliness. The CO2 concentrations go up and down, and they don't go up to the exact same amount every time, but it's pretty clearly cyclical. And they never went above 300 parts per million. And they also never went up this fast either. And carbon dioxide is controlled in the atmosphere by amounts of subduction and by biological activity. Humans have a disproportionate influence on Earth, and it appears definitely that we have caused this massive increase in CO2 by burning fossil fuels. There's no way to interpret the data otherwise. Carbon dioxide is not the only greenhouse gas that's of concern, however. And the simplest of the hydrocarbons, or compounds made of almost entirely of carbon and hydrogen atoms, is CH4, which, unlike most hydrocarbons, is actually a gas. Methane is kind of thought of as the stinky gas because it's what's in flatulation. It is also a potent greenhouse gas, and the chart on the upper right shows the degree to which greenhouse gases absorb different wavelengths of infrared light. CH4 doesn't absorb a particularly wide range of infrared light like CO2 does, but you'll notice that the CO2 peaks are not very high. It doesn't absorb that much radiation. CH4 can absorb a lot, in part because it's a more complex molecule than CO2, and it can transform and bend in multiple ways. So methane, a single methane molecule can trap a lot of energy and release it back to Earth as radiation. And methane is a component of natural gas, and it's usually released when natural gas is extracted. It's also released by decaying landfill and by livestock when they burp and flatulate. And another thing of concern is that a lot of methane is frozen as ice in what is known as the permafrost, which is the frozen layer of soil in places like Siberia and Alaska. The permafrost is melting presently. Now, remember that greenhouse gases aren't only sending radiation back to Earth, but a lot of it, but excuse me, they're not. The greenhouse gases are sending a lot of the infrared radiation back to Earth, and without that, a lot of the radiation would go back to space. Greenhouse gases keep the planet habitable, but even small changes in their concentration can have a noticeable effect on how much radiation gets trapped, and that will affect patterns of ocean and air circulation, and more greenhouse gases will make the planet warmer. So the vast majority of the CO2 added to the atmosphere comes from burning fossil fuels. And this diagram shows you that when you look at the strongest sources of carbon dioxide, you compare all sources of carbon dioxide to fossil fuel emissions alone, they're more or less the same map. CO2 emissions are by and large coming from burning fossil fuels. And you'll notice that the highest concentration of emissions are in highly populated areas because those are places where you have factories as well as a large population that in many cases has to transport themselves a long way to commute. So cars release CO2 by burning gasoline. By the way, this map, the satellite I think was focused on the Northern Hemisphere, which is why you just see nothing in the Southern Hemisphere. I will say that there's definitely more industrial activity overall in the Northern Hemisphere than the Southern Hemisphere, but that's why it's completely blank on the South, because the satellite was focused on the Northern Hemisphere. But anyhow, the fossil fuel emissions are the largest source of greenhouse gases, but we also have some other things of concern, and some of those other sources are especially concerning because they have the potential to release lots of methane, which again is a stronger greenhouse gas than CO2 because it can absorb much more strongly than CO2 can. And the amount of grazing of livestock has increased heavily as demand for meat, and particularly demand for beef, has skyrocketed. That's soared with industrialization and with the spread of fast food. A lot more land is being used to graze cattle, and there simply are many more cattle than there used to be. And cattle produce methane when they burp or fart because they have a four-chambered stomach that allows them to process grass and other cellulose-containing plants. There are simply a lot more cows and other ruminants, or sheep and goats and their relatives, than there were a century ago. And this has had a pretty noticeable effect on how much methane is being released. Also, clearing forests for pasture has played a role in accelerating climate change because trees are long-lived and they sequester carbon for long periods, but if you cut them down and replace them with short-lived shrubs and grasses, you not only have cows producing methane in that area, but you don't have long-lived woody plants that can take up CO2. Additionally, in areas south of the Arctic, like Alaska and Siberia, there is a frozen layer below the uppermost layer of soil called the permafrost. And it's mostly water ice, but it also contains frozen methane. And permafrost has been thawing in a lot of the Arctic. This has been releasing methane, and this is an example of a feedback cycle in which an effect brought about by global warming, the permafrost melting, is actually speeding up global warming as well. There's also the fact that landfill, aka just garbage piling up, is producing methane as it decomposes. That is one good reason to reduce garbage production, because burying garbage produces methane, and a lot more garbage is being produced by human waste and by industrialization, and a lot more land has been converted to landfill. Humanity is producing more garbage than it did 1,000 years ago, and that is having a pretty significant effect on how much methane is ending up in the atmosphere. So greenhouse gas emissions are largely from burning fossil fuels. The electricity production largely comes from that, from coal-fired power plants. Transportation comes from burning gasoline, and then industry also that's largely from coal. And then you have fossil fuel emissions related to agriculture, and some of that's from cows, some of that's from, say, the cost of transporting food. But anyhow, this gives you a sense that actually the amount of fossil fuels that are used by people living in their homes and at their businesses is relatively small overall. That's not saying that making homes more energy efficient has no place or no help at all in reducing fossil fuel emissions, but a big change has to be made in how we produce electricity and how we get around to make a significant effect on how many fossil fuels we're burning and how much CO2 and methane is ending up in the atmosphere. And I will continue on with the discussion of global warming with the carbon cycle in the next part of the lecture. And that is my cat walking across the screen.